Okay, so we have the Earth and the Moon with a spaceship in between them, directly in the middle. Now, look, in this problem, the textbook doesn't do a good job, in my opinion, the textbook doesn't do a good job of specifying center to center. To me, the way they say the average distance separating Earth and Moon is 384,000 kilometers. To me, that kind of sounds like from the surface of the Earth to the surface of the Moon, So do you have to look up the radius? You know what I'm saying? Like, do you have to add the radius of the Earth and the radius of the Moon? Turns out that what the textbook means in this problem, when they give us the distance of 384,000 kilometers, they mean from center to center, okay? Which is important. The equation that we're going to be using here, all objects in the universe are attracted to each other. Whether they're good looking or not, they're attracted to each other. The equation is G, big G, which is a gravitational constant, m1, m2 over r squared. This r is center to center, from the center of m1 to the center of m2, or whatever the masses might be, m1 and m3, whatever the two masses are. And G is the gravitational constant. You don't have to memorize this. I'll always give it to you. G is 6.673 times 10 to the negative 11 Newton meter squared over kilogram squared. That'll be a given. Okay, so how do we go about solving this question? They want us to find the net force, find the net gravitational force exerted by the Earth and Moon on the spaceship. Okay? So how many forces are acting on this spaceship? Well, look, is the Earth an object? I'm going to say the Earth is m1, the Moon is m2, the spaceship is m3. So let's just forget about the Moon for a second. Just totally forget about the Moon. Is the Earth an object? Yeah. Is the spaceship an object? Yeah. So what's the Earth doing to the spaceship? Pulling it, right? That's a gravitational force. Now, is the Earth also attracted to the spaceship? Yeah. But we don't care about that force. We don't care about this force because why? Which object are we focusing on here? We're finding the net force on what? On the spaceship. Okay? So the Earth also has a force, but we're focusing on the spaceship. So I'm going to label this force F31, meaning what? The force on object 3 from object 1. F31 meaning the force on M3 exerted by M1. Okay, is the Moon an object? Yeah. The spaceship's an object. What's the Moon doing to the spaceship? Attracting it. So we're going to label this force F32, meaning what? The force on object 3 by object 2. Now, is the spaceship also exerting a force on the Moon? Yeah, but we don't care about that force because we're focusing on the spaceship. All right, now, are these two forces here, are they going to be perfectly equal? Are they going to cancel each other? In fact, before we do any calculations, which of these two forces will be bigger? Will F31 be bigger or will F32 be bigger? So look at this equation up here. Here's our equation. Which force is going to win? F31. Why is F31 going to win? Because the Earth has a larger mass. Okay, so basically from here, what we're going to do is we're going to calculate each of these forces. So let's find F31. Let's find F32. Once we know these two forces, are we going to add those two forces or what? Or subtract them? We're looking for the total force. Think about this like a tug of war. It's a tug of war on the spaceship. So once we find F31 and F32, do we add them or subtract them? Subtract, because they point in opposite directions. Okay? So F31, here's how you do it. So we're plugging into this equation. So we're going to go G So it's going to be 6.673 times 10 to the negative 11 Newton meter squared over kilogram squared. All right, so we're doing M. What are the two masses for 3? It's going to be M3. So that's going to be spaceship, which is 3 times 10 to the 4th. We're basically taking this mass and this mass, right? Those are the two masses. Mass of the Earth, 5.98 times 10 to the 24th kilograms. And then, now, what's the distance? Is this going to be our distance? Nope. That's the total distance from the Earth to the Moon. So what distance do we need to, what do we have to do to this number? Chop it in half. So we're going to go from there to the center of the spaceship. So this comes out to be 1.92 times 10 to the 8th. 1.92 times 10 to the 8th. We got to split that distance in half. So this would be 1.92 times 10 to the 8th meters. And make sure you square it. Guys, I cannot tell you how common it is for kids to get problems wrong because they forget to square. The distance of separation is squared. So F31 comes out to be 324.74 newtons. All right, now we find F32. So F32, which is going to be this force, the force of the moon on the spaceship. So we're plugging in again, 6.673 times 10 to the negative 11 Newton meter squared over kilogram squared. All right, so now we're doing this mass and this mass. So this will be 3 times 10 to the 4th. The mass of the moon is 7.36 times 10 to the 22nd. And then the distance of separation from spaceship to moon, 1.92 times 10 to the 8th. So this gives us a force of about 4.0. Okay, so F32, this is 4 newtons. F31 is basically 324.7. So what's going to be the total force on the spaceship? So here's the spaceship. What's the net force going to be? The net force is going to point towards the Earth and equal what? What do they round this? Is 320? What does the book say? 321. 320.7. That's the answer. The net force is 320.7 newtons.